The time travel debugging for high-level synthesis code. Abstract. High-level synthesis HLS code is often developed using subset of the C and C++, along with specialized libraries. This allows the HLS engineers to make use of the standard software engineering tools and techniques during the development and debug phases of their project. This paper introduces the topic of the time travel debugging, whereby the state of the design can be examined by going backward and forward in time. This approach saves a huge amount of effort aligned to the root cause of bugs, and including challenging concurrency bugs to be found with the state and new code base to be understood rapidly. Furthermore, it's possible to extract waveforms from a time travel recording, and thus allow the LS implementation to be analyzed style more familiar with many hardware engineers. We explain the application of the time travel debugging to HLS designs and the advantage of ability and limitation of this approach. Introduction. The high-level synthesis HLS is design process whereby the behavior of solution is specified at an architectural and algorithmic level, typically using a subset of mainstream software programming languages such as C or C++, along with libraries such as SystemC. Several widely known advantages of writing hardware designs in C or C++ include faster testing and development by the running natively compared to a traditional simulation-based testing, and the target difference power performance area PPA configuration from the same code by the turning the synthesis tools configuration. There is too a less well-known advantage of writing hardware design in C or C++, the ability to use industry-standard software engineering tools and techniques. This is the widespread availability of the verification tools. For an example, the coverage tools such as G-Cove and memory checkers such as Helgrind, and various sanitizers such as ThreadSanitizer and ThreadSanitizer. This considerably improves the quality of behavioral model and add an extra dimension of validation on the top of the final hardware description language HDL verification stage. At the development of a state debug stage, a designer can employ a standard debugger such as GBD. Traditionally, bugs with HLS designs are found using brute force techniques such as logging values to a file. It can take a long time to review a log file, and adding more data to the output requires rebuilding the code and rerunning the test case. Debugging this way is very time-consuming and does always find the root cause of the issue. The object of this paper is to introduce a powerful and yet still known and techniques of the time traveling, the debugging being to able to debug both forward and backward in time, and demonstrate how it is particularly well suited for analyzing the HLS designs. Chapter 2 is what is time travel debugging. A traditional debugger is a computer program which is used to control the flow of another executable. The debugger monitors the execution of the program being debugged, allowing for each execution to be posed in the IR points and for registers, variables, memory, and examined to this point, and for the executable to be resumed until another DIR point. Time travel debugging provides a significant improvement by enabling the developer to move forward and backward through the execution of the application at will to quickly home in on issue. A time travel debugger records the execution. It proceeds importantly save the result a non-deterministic event, including system call, that is, user or kernel space interactions, and a memory mapped device register accesses. During the debugging, the execution can proceed in either forward and backward reverse direction. The debugger will use its recording and knowledge of the non-deterministic event to be re-execute the program in order to recompute memory and the register values for any desired point at the program execution. These non-deterministic events typically represent a tiny fraction of the instruction executed, meaning the recording of the operator is relatively small. And the time travel debuggers can also make intermediate snapshots to improve the performance for developer. Time travel debugging is being rapidly adopted in the software industry by developers of large and complex code bases. For example, all the major EDA companies making extensive use of the time travel debuggers. Developers are often faced with exceptionally large large code bases, the code discovered in section 3. Non-executable intermediate failures see the repeated run as part of the regression flows in section 4. Section 6, and how to find the concurrency both in the example in section 5. Time travel debugging helps enormous in all these situations and more. Chapter 3 is an overview of the time travel debugging techniques. The powers to operate of both forward and backward, but especially backward, can be seen from table 1. A very common question is how did the value of value change? To debugging this is simply a case of executing until the point of failure and using the last command. Often it is necessary to fully understand and code from the data changing to the failure being found to solve the problem, thus saving substantially developed time. Table 1. Traditional and reverse debugging operations. Another significant advantage of the time-traveling debugging is in code discovery. Sometimes it's interesting to ask questions. How did the execution get to here? Or why does this algorithm do that? Is being able to step forward and backward through the code age, learning about parts of implementation which matter to the particular problems. A good time travel debugger allows the user a set of bookmarks that map to the flow of code through the time and usually into a certain point in the flow. Furthermore, it's no longer possible for developers to become lost when the program is unexpectedly hit or does not break point. When this happens, this is common while debugging an unfamiliar codebase. The developer can simply jump back to where they previously were and try again. A time travel debugger can be run as a standalone command line application, suiting those familiar with standard debugging approaches. It can be run also in a integrated development environment, often facilitating the learning curve of tools with the application host either running locally or remotely, therefore suiting any computer setup, or for example, using a plugin in Visual Studio Code. Additionally, the technique for the thread fuzzing that can be employed. This allows the debugger to alter statistics of the thread scheduling, for example, the starting thread, minimizing the execution slot granted to certain thread, and minimizing the scheduling order. Preempting the thread is a known well-challenged cases. For example, in places where there isn't usually a jump instruction or just before and after locking operations. And in a feedback directed manner to the force scheduling and or starvation and execution point where shared memory style modification occurs. Chapter 4 is applying time travel debugging to the HLS. HLS style behavior models are typically architected to have many small execution units operating in parallel. In SystemC, it's quite common for models designed to have a method, thousands or even tens of thousands of SS threads and or less methods executing at the same time. Such parallelism increases the probability of the both common to multi-threaded application. Race condition threads simultaneously access to shared data and deadlocks the threads mutually inescapably blocking each other are easily introduced. Sometimes these can be prevented using formal techniques. However, they often requires an understanding of where the issue may present itself. For example, that one has already located the bug or using customer compiler. Other common issues are very difficult to isolate using traditional techniques such as many corruption, intermediate bugs, and incorrect result. 5. Chapter 5 examples. In this section, we present how a developer might use the time travel debugging to find the location of incorrect value being stored in memory. We then discuss these techniques as applied to race condition and deadlocks and code exploration. Finally, we provide a simplest example to see how rapidly we can find both using time travel debugging. This example makes use of this example in the acceleration SystemC reference code. Let's just say we get a stage 2 in our debugging where we know that the incorrect values is being stored in data. This point in the code And the point of the example is to be sure that we don't need to understand much of code to find the location of the bug. The yellow arrow that denotes that exception is stopped at this point where the value of the data is being updated with the incorrect value from MEM. We now have 2.4 bug. By considering the questions on the data, the MEM, incorrect or is the addressing into MEM wrongly calculated. In practice, we must guess which is most likely and note the fork in the debugging process to return later if we hit the dead end. We could bookmark this point in time in our debugger to return easily later. Here, we will start with the data corruption options each guess. We can find out the MEM data was last changed by the entering the command last MEM address minus m underscore start underscore address divided 4. It's also possible to do this through the GUI. The last command that sets a watch point on the data in the interest of continuous execution in a backward direction until the data were last modified. And then this shows us the debugger back execution until the data at MEM changed. When the program was running forward at this point, it updated the data at MEM from 27 to 38. Having now found where MEM was modified, we can go step up the course to see that data here is the asterisk data. Star data here is the data passed in through the request. So we see the my data I plus equal I increase by I is the line of the code of the interest. The understanding phase can now start to compare what the area of code should do and what it currently does. Note that we found location of the problem very quickly. We didn't need to worry about what the intermediate code was doing. We didn't need to keep track of the many threads running in parallel. We let the debugger handle the complexity for us. We were able to follow the data flow backwards at several steps and easily identify the root cause of the problem. Had we gone down the wrong path in our debugging, that wouldn't have been a problem either. We could have jumped back to the bookmark or move forward and then tried backward without restarting entirely. The race condition can occur when the multiply tasks execute concurrently, with correctness being dependent on the order of event. For example, say two threads are trying to increment the counter. It is critical to read an incremental and write back steps for each thread until they interrupted by the other thread. Otherwise, this might both increment the counter the same value. That is, the thread 1 read or thread 2 reads the same values, and then both thread incremental from the same value. In a real hardware design, a simple example is a shared arbitrated data bus. For example, if data being mixed from multiple sources and transmitted from the wrong source. In HLS design, it can often be preferable to avoid the use of data access controls, for example locks or mutexes, as they can increase the latency and area and reduce the throughput of a design. It's precisely this desire which increases the chance of the race conditions occurring in complicated HLS design. The race conditions can be notoriously difficult to solve. Some race conditions happen sporadically, so it can take time to find a failing case, and when we do, we want to be able to debug without losing the context. This stops us adding the extra debug later, for example for the logging. A time travel recording of a failure event is perfect. There can be a huge number of operations between the error that can same error being noticed. Typically, several tools are used to find the race conditions. Static analysis tools, for example, Coverity, can identify certain classes of race conditions. Such tools can be expensive and suffer from the false negatives. They don't guarantee to catch all such issues and false positive. They often flag problems that aren't really problems. Dynamic analysis tools, so for example, ThreadSanitizer and Helgrind, can identify certain races deadlocks by flagging if one thread writes memory after another thread to write the same memory before any thread has read it. This could be a great clue, but it could be a false positive. Also, that they tend to be most useful to foreshadow trivial race conditions, such as an obviously missing lock. Often such tools offer little help in identifying the root cause of such places, merely that such places exist. Some tools can slow down a program by 10 to 100 times, which in turn could be enough to prevent the race condition occurring. Logging output can help a developer identify what a problem is doing and pinpoint issues in the flow. However, the logging often takes up an enormous amount of the disk space. It's time consuming to read, typically requires several attempts to get the right values outputted, and can also slow down a serialized execution to a point that a race condition does occur. Heinsberg. Time travel debugging works reliable for race condition. Once a value has been noted being incorrect, the developer sets a watchpoint in a variable, so the debugger stops whenever the variable changes. By continuing the execution in reverse, the developer can see when the value is changed and quickly build a watch picture about the sequence of the modifications. Critically, the developer doesn't need to understand what all the concurrent threads are doing, not to understand the entire code base, and to navigate backward to find the cause of the failure. Typically, a developer can quickly find non-atomic accesses to data in this way and then know immediately the type of unsafe programming patterns in the design to be fixed. For example, by adding the locking or re-architecting to guarantee safety without locking. That lock occurs when two or more threads are blocked waiting for a resource, preventing themselves from sending or freeing the same resource. A simple example in a real hardware design is the two modules with the handshake mechanism. Module A is waiting for a token from a module B, and in parallel, module B is waiting for a token from a module A. Both modules are blocked by each other from proceeding. In SystemC, deadlocks can be readily introduced design where the SS thread are synchronized by waiting on, notifying where the SSB event and or using a SSB mutex type lock to control data access. The same data deadlock pattern is seen using the other HLS primitives. Using a time travel debugger, deadlocks are relatively simple to debug. The debugger is attached at the point when execution, at least in the offering thread, has stored. The developer can optionally look through the backtrace for the thread to see which threads are stored. The developer sets breakpoint at the points where the code needs to wait for a resource, for example, a lock function, and where the code would free the resource, for example, an unlock function. The developer executes the code in reverse to understanding the probability sequencing, leading know their deadlock and then sense of the issue by facing the bug and re-architecture resource management as appropriate. Often, engineers are tasked with adding feature, debugging an issue, and joining a team to work with a part of a large code base with much of which they are unfamiliar. Using a time travel debugger, an engineer can start from a point of code in the middle of the execution and set break point. Execution can proceed in either direction to this breakpoint, from which point the developer can explore how the execution reaches this point, the value of variables in memory at this point in time, state of the other thread at time, and it can use watchpoint to understand where variables in memory are modified. The good time to travel debugger offer the features to bookmark a relevant point in code in time, further allowing engineers to understand how the flow throughout the execution. There is no possibility of the developer debugging becoming lost and having to restart a long debug session over again. They can always get back to the familiar territory, like hitting the back button on web browser. The chapter 6 is the HLS debug best practices. Many time travel debuggers offer the facility to record a failure and debug it after the event. This is powerful as it allows users to debug an issue without having to reproduce themselves. For example, debugging a customer's failure, debugging a regulation failure without needing to check out the exact code version, and debugging an intermediate failure. Time travel debugging should be built into regression flow. It can take a long time to run through a set of the tests, some of which might only present intermediate failure. In some setups, reproducing a bug can involve the lengthy process of checking out the code and write revision along a build and test cycle. A regression flow knows when a test has failed. This test can then be rerun through on time travel debuggers, recorders, and failure recorded. The engineers can now simply connect their time travel debugger to the recording to start on the issue. No need to reproduce the bug directly themselves. Sometimes the test failure intermediately, in which the case failure recording attempt might need to repeat it multiple times to get correct recording, or all the tests could be recorded at the expense of some disk space. Engineers should write their code thinking about the design for debug. It's helpful an input error can be detected within the same executable at the time which would need to debug. Some systems run a test which output a file and then compare their output files with the unknown reference, flagging an error where difference is detected. Consider instead of re-architecture so that the executable list is unknown. Reference itself flags an error internally. Should there be a difference between the executable output and the reading reference? In the latter case, the debugger can stop their first detection of error, and the watchpoint or last command can be used to discover quickly where the erroneous value came from. The bug is isolated. Intermediate values can help debugging. For example, the intermediate timestamp calculation can be used to set a conditional breakpoint during the compilation to HDL. These variables will be optimized out, meaning that this approach as the benefits does not harm the final synthesized output. Assertions should be used readily to act as sanity checkers for assumptions made within the design. If during test failure or needed a successful test, an assertion fires, the engineer debugging it already has a very good starting point. Put the execution in the debugger at the point where the assertion fires and the debug backward to understand why the assumption was falsified. Chapter 7 is waveforms. It's possible to extract waveform from a SystemC program to analyze in a style more familiar to many hardware engineers. The image below shows screenshot of a GTK wave displaying the output of one HLS SystemC example configuring the dump of VCD file. It's also possible to extract waveforms from a time travel recording without needing to rebuild or relearn the executable. This provides powerful options for hardware engineers, especially those transitioning to HLS design and implementation. A waveform viewer can be linked to a time travel debugger so that by clicking on transition in the waveform view, the debugger can synchronize the point and the time travel recording where the transition occurs, allowing the full time travel debugging starting from the same moment. Chapter 8 is public availability. These are several time travel debuggers publicly available. HLS designs are most commonly used in the C or C++ base language, often including associated libraries such as SystemC. The most useful known time travel debugger for HLS engineers are the Linux RR and Undo, Windows Microsoft Time Travel Debugging Tool. Each time travel debugging listed above offers support for either Linux or Windows and offers a different set of the features and different performance. Section 9 is a limitation. A time travel debugger as for a traditional debugger presents a small performance slowdown, but how much depends vastly on the workload. However, in practice, a good regression systems can be compiled to record the failure test offline, ready for a later debug. The overhead of a recording size depends on the length of the execution and the number of non-deterministic event but tends to be relatively very small compared to typical HDL simulation log files. Thread fuzzing, as discussed in Section 3, is implemented standard OS threading mechanism. For example, Linux pthread, HLS tools and or libraries often of their scheduler as an HLS design might have thousands or even tens of thousands of threads running in parallel, so using a standard OS primitives could be too slow. As such, the thread fuzzing supplied with a time travel debugger wouldn't work out of box, but could be implemented by modifying the supplied scheduler where a source code is available. The examination of thread info is discussed briefly as an option step when solving deadlocks in Section 5. The same reason as for thread fuzzing, this thread information isn't available directly from a time travel debugger for HLS tools or libraries using their own threading module, but could be extracted by looking through the scheduler data structure, again where source code is available, or ensuring a standard Linux threading module, that is pthread, is used. Section 10 results. Qualifying the time saved by using such techniques is challenging. It depends on the bugs to be found and code base to be understood. We haven't seen a data suggest that finding a bug is often at least 4 times faster using time travel debugging than traditional techniques, and sometimes significantly faster still. This 75% reduction in time spent finding bugs and the speed up of learning code leads to a significant improvement in effectiveness of the engineers working on a project. This enables faster time to market and more time to implement additional features, to add additional coverage closure, and to enable more abstract application layers to be brought up before silicon is returned. In short, enabling the advertised benefits of the shift left. Further, by being able to complete an HLS design faster, this feeds well into a shift left paradigm, and whereby the HLS implementation can be tested with the entire software stack running natively, say on x86. Then against the FPGA synthesis of the same implementation, both significantly for tape-out, and then finally against the silicon production version of the same implementation. When used for modeling the reduced debugging time, leads in turn to increase the throughput and can result in a wide range of scenarios and applications being modeled, and thus result in more inefficiency being discovered prior to chip tape-out, and so result in improved PPA characteristics. So to chapter 11 is conclusion. We have demonstrated that it's beneficial to apply standard software development tools and techniques to HLS development. We have shown that a concept of time travel debugging, which allows the flow of the executable and big executable both backward and forward in time, vastly simplify the task of the debugging and code discovery. We have highlighted in the improvement in effectiveness can be directed to the faster time to market, better early testing of the implementation through the shift left. One of the key advantages of HLS is able to take advantage of the advanced tooling that is available to software developers. Time travel debugging is particularly compelling. Finally, producing waveform views of recording allows the debugging flow with which digital design engineers are more commonly familiar, and so aids the transition to HLS. Acknowledgement. The authors write thanks to References. There are so many references, 1 to 23. Okay. Good references. Okay, today I read this paper, Time Travel, Debugging for High-Level Synthesis Code from DVCON2025. Thank you for your time. See you next time.